Hello, everyone.
Hi.
I already introduced myself earlier. Now I'm in another room, which is the control room, much better lighted than the previous one. And this is courtesy to Zoltan that you heard before, and Noemi, who are our virtual visit masters here at CMS. Next to me is Aurora. She is also going to be a guide during today's visit.
Hello. I'm a PhD student with the University of Milano Bicocca in Italy, and I'm based at CERN for the PhD, and I will stay on the surface with you.
So I will first introduce you to the control room, which is where we are located right now, after which I will slowly head out to the elevator area, which is the place from which we descend to the underground, where the experiment is located. In the meantime, there will be short intervals during which I'll lose connection and you'll be able to talk to Aurora during this time. But even as we present things, as we show things and explain, you can interrupt us at any time to pose questions. I hope we'll have even a time for a Q&A session at the end, during which you can pose even more questions or something that you didn't understand during the visit, something that you found curious, etc. So I don't know how much context you already have about the CMS experiment. I assume you already heard something during Atanu's talk about it. But as today you're going to be analyzing data from CMS, I think this would be the perfect start of the day to first see things in real life, where this data is collected, and then you can play around with it during the remainder of the day. So Noemi, maybe we can do a tour now of the...
So we'll have a quick tour of the control room. It is the place where 5 people stay 24/7 during the data taking. To ensure that all the data are collected correctly and everything goes smoothly. Okay, while we set up,
Okay.
we will. It's okay?
Yeah, I
Okay.
think we're all set up now. So currently we're located in what's called the central area of the control room. You see this semicircular area here. We have several shifters who are on duty currently. As Aurora mentioned, we have people in the control room 24/7 during the times of data taking, which is currently ongoing. So I'm going to start one by one and explain in a little bit of detail what each of these shifter stations are intended for. The first shifter that we are going to look at is the technical shifter. As you can see, they have a whole bunch of screens in front of them. What they are responsible for is mainly the detector control system. This is a system which allows us to control the detector, as the name suggests. That is, we can power it on, power it off, exclude subparts of it in case of need, etc. They're also in charge of the detector safety system. This is a system of sensors which augments the data of many sensors that we have in the underground and on the surface, and which notifies in case something goes wrong. Apart from this, they are also in charge of the access system. So you're going to see later when we enter the elevator area that there is a biometric reader there which allows us to identify ourselves and to be let inside this area. The technical shifter on the surface monitors at all times who goes in, who goes out, how many people are in the underground, etc. Of course, what helps them the most in this monitoring is all of these CCTV cameras, which gives them access to the whole infrastructure here at CMS. Then we move on to the shift leader, who has fewer screens in front of them, but as the title of the shift position suggests, they are the person who leads the shift crew. They are the person who coordinates the actions which go on in the control room. Also, they serve as the contact point between the control room and the outside world. Next to them, we have the DAQ shifter, typically pronounced DAC or DAC. That's why the symbol of the shifter station is the duck, and we have all of these little rubber ducks lying around. They are in charge of the data acquisition process, so they have to be in the control room while we are taking data. So you see many graphs on their screens. These indicate mainly the data rates, so the amount of data that we are collecting and the kinds of data that we're collecting at any given moment. Then we move on to the trigger shifter station. This is one subsystem of CMS, which serves for filtering the data and choosing only the best data to store. When we go in the underground, I'm going to show you where exactly the hardware that belongs to the system is located at and how it works. I'm going to say a few more words, but basically the idea is that we collect too much data to be able to store them all. So we need to have some strategy of choosing the best, the most valuable data. And this is the purpose of this system. So that's what it does. It filters out all the, let's say, least interesting events and keeps all the best ones to store them and to process them further. Then we arrive at the final central shift station, which is the data quality monitoring. This we see that currently we have no shifter here. They are remote from Fermilab, so very close to you. They are the people who take a look at the data as it's coming in real time as it's being collected. So their main goal is to make sure that the data that we are collecting is of good quality. All right, I think that summarizes more or less this central area. And then outside of the central area, we have many other stations where the subsystem experts are seated during the day, especially in the mornings. You'll see a lot of activity here because people are planning what's called the plan of the day. So each morning we establish what is the plan for that particular day. So you'll see a lot of experts trying to set up this plan every day. Now in the afternoons, as this is established and the data taking is smoothly ongoing, this is a quieter area. And the central shift station is where most of the activity goes on. Any questions here? Any curiosities about the control room? Is this what you expect from a control room, or was your image of a control room more like the NASA control rooms from the movies? All right, you can think of questions. Yeah.
Yes, we have a question here, Elton.
Please go ahead.
Microphone here. If that's how the day-to-day is when you're collecting data, how is it when you're not collecting data? Are you just analyzing?
Yeah, that's a very good question. So what's known as a technical stop is what you're referring to. So for several months a year, we have a period of inactivity in data taking, but this doesn't mean at all that it's an inactive period. Quite on the contrary, it's actually very active, and there are a lot of people in the control room as well during that time. That's because this is the period of time when we do all the maintenance, the upgrade, and all the service work on the detector. So periodically, so once a year, we have this window of several months, and periodically we have short technical stops during which we perform this work. Then on the side, people will do analysis. Of course, analysis doesn't go on in the control room. This is done outside, of course, yeah, offline, as it's called. Yeah, any other questions?
We have one more.
Sure, go ahead.
Why is there so much security to get into like the place where you need to do the experiments?
What do you mean by security? Are you referring to the safety features that I mentioned earlier?
like the elevator and you have to all like the cameras and you have to like a biometric like lock on there? Like, why is that so secure?
Well, obviously, you want to keep track of who goes in the underground at any time, right? During times of collisions, nobody can enter the experimental cavern, including us. We won't be able today to go to the experimental cavern. We are only going to be able to access the service cavern, which is one floor on top of it. The reason, I think it's quite obvious. I mean, you simply don't want to just anyone walking in into the service cavern, or much less the experimental cavern. First of all, for the safety of the people, but also for the safety of the equipment. You want to have qualified people going into the places of work. And whenever it's someone from outside who goes for a visit in the cavern, we need to have a qualified person, a guide who is trained appropriately to guide them there. Yeah. Does that answer your question?
Yes. How deep underground do you have to go to get?
I'm not going to answer that now. You're going to see there's a live display on the elevator which shows you. So, yeah, and maybe we can get moving and start getting there. Let me just get my helmet. So I need to bring the safety equipment with me.
Okay, while go in the direction of the elevator, I will show you where we are now. You see the picture with the yellow circle, that is the LHC. And we are on the left, where you see CMS here. We are in France, but close to the border with Switzerland. You see in the background the Lemon Lake, Geneva, and Mont Blanc here. On the other side of the ring, we have the Meran site, which is the main site. And it's where most of the people work. So we are like 10 kilometers away from the main site in the fields. So you see now him entering the for security control, say. There is a biometric control to check that which person is entering specifically. And the object that you have just seen is the dosimeter that checks how much radiation a person is getting by going down. Because also now that we have collision, there is some radiation. So we have to check that the radiation dose is not too elevated. In any case, it's not that high, but for safety, we have to ensure that. And as you have seen, only one person at a time can enter, so that we are sure that of the amount of people that are getting inside. Now, this is the one of the two elevator.
We can see now the depth at which the elevator is located at right now. This is the furthermost down that the elevator can go. We're going to call the elevator now, and you can track in real time how quickly it comes up. So this is level -3, where the elevator was. That's where the experiment itself is located. There are 2 more floors on top of it, which are part of the so-called service cavern, -2 and -1. -2 is where we are headed now.
Yeah, and then in -1 we have other hardware equipment for the trigger that you have seen to take data.
So while we're preparing to enter the elevator, I'm putting on my safety equipment. In order to go into the underground, I have to be equipped with 2 safety features. The first one is the safety helmet that you see me wearing it now, and also the safety shoes. So these are regular working shoes, but which have these steel pads on top of the toes, not to get hurt. So now I'm pressing -2, and I believe we're going to lose connection soon. So maybe Aurora, you can take over and show some more images.
Okay, let's go, and then now that you've seen where we are, we can have a look at the underground where we are going now, and you see that we have the LHC ring, which is roughly 100 meters below the ground level, and this is because we needed a stable surface to put the detector, and most of the surface above that is morass, so it's not stable enough. And as you see, we have here CMS, and we have two different shafts to go down. I think we have, yeah, exactly. We have two different elevators to go down, and we will go in what is called the service cavern, which is this one, and which is right next to the experimental cavern where the experiment is located. But they are separated by a lot of cement, and you see here the path to go there is not a direct path, but does some curves in order to prevent the radiation from going into the service cavern. We are at -2. So we have reached the level where we have
so we have arrived in the service cavern at level -2, and we are entering. So the first thing we can see here is this huge shaft, which is the elevator shaft, and the stairs which are next to the elevator shaft. These stairs are not meant to be used strictly, so they are there obviously for cases of extreme emergencies, just as a safety precaution, but they are not meant to be used on an everyday basis, because you can imagine going 100 meters up. So that's a lot of walking. You need to be very fit, and it takes like 25 minutes to do it, even when you are. Apart from that, we can see this light beaming up in regular frequencies here. Do you have any guesses maybe as to what this is or what it represents? Okay, yeah, if we have any guesses, you can say it. I'm going to spoil the answer. So this is just a representation of the data that we're beaming up each moment. Of course, the frequency with which we beam data while collecting it is not the same as the frequency of this light, but it's obviously a representation of it. The real frequency is actually much higher. In the LHC, we have collisions happening each 25 nanoseconds, which amounts to 40 million times per second. So you can imagine that you have events happening 40 million times per second. And if you send all of this data up, it would need to be done this many times a second. I mentioned earlier that we have one subsystem, which is called the trigger station, the trigger subsystem, which allows you to filter out the least interesting data and only to keep a small amount of it. Just as an exercise, think about this. Each event, as I said, 40 million events per second, each one of them is of a size which isn't that big. It's like 1 or 2 megabytes. But think about how much data it amounts to every second. So it would be in the tens or hundreds of terabytes per second, which is almost impossible to handle, not only in terms of bandwidth of transporting it, sending it, but also storing it and processing it. So that's why we have this system in place, which allows us to only choose the best data. So now I'm moving into the next room. Yeah, so maybe we can stop here for a second. we see many consecutive racks of electronics just next to each other, and a lot of cables going into these electronic modules and coming out of them. This is part of the detector safety system that I mentioned earlier. So all of these fiber optic cables that you see, they are actually data from these sensors, which come from the experimental cavern. And they give us an idea at any time of many parameters, mainly environmental parameters. So we know what's the temperature, what's the pressure, what's the relative humidity at any point in the experimental cavern. But also we have all sorts of sensors like fire sensors, water sensors, oxygen sensors, and so on. So we have at any point in time a clear idea about the state of the experimental cavern, and any value which exceeds some predetermined allowed intervals would trigger an alarm, which then would go up to the control room and would show on those screens that we saw earlier in front of the technical shifter, and they would need to investigate and send people, experts, to go and check out why this alarm was produced. Moving on to these next rows here. I mean, they look similar, but they have a different function to the previous one that we showed. This one is the one that I have mentioned several times, the data acquisition and the trigger one. So all of these fiber optic cables that we see around here, they are the ones which are bringing the data from the experiment itself to this room, where it's pre-processed and filtered, and then it's beamed up to the surface where we have a second room like this one, which does then a more sophisticated, more thorough processing. Yeah. So for now, we have assumed that we have all of this data coming in and we are processing it and we are filtering it. But actually, in order for the detector to work, we need to power it. And all of these cables that you see on this side, they are actually supplying power to the detector. So different subsystems within the CMS detector are based on different technologies, and they work on different power voltages. We have muon chambers in the muon system. So these are the outer layers of CMS, which actually operate on up to 10 kilovolts, which is a very high voltage. And these cables that you see are the ones that are supplying this voltage. Then in the innermost part of the detector, we have more sensitive silicon technology, which operates with a few hundred volts. Apart from this operating voltage, we then have the low voltage supply, which supplies all of the electronics, which does the readout of the data, which then comes here for processing. Okay, so I think we can see one more part of the service cavern now, as we slowly descend down these steps. So here we're now approaching the furthest most point that we can access in the current conditions. The reason is, as I already mentioned earlier, that we have proton-proton collisions going on at the moment, somewhere around 15 to 20 meters in that direction, slightly downwards. That's where the detector is located. So if this were to be times of a technical stop, we would be able to enter through here and then just go take a left here, and there's a tunnel which takes you to the experiment. Now we see that nobody is allowed to go through here. You might have noticed, or might not, that this door is actually of a different color than the one in the surface, which we took to enter to the elevator area. This one is yellow, and this is a color code which actually means something. It means that if one were to force this door and for some reason enter then in the experimental cavern where it's not safe to enter, this would immediately automatically abort the beam. So this is a safety feature just to prevent even the most extreme cases of non-compliance with rules. So, and also a camera, but the best way to stop someone getting hurt, obviously, is to abort the beam. So, as I said, the detector itself is located maybe 20 meters with a huge wall of concrete separating us from it. And the magnet is at the center of it, which makes it even a bit more that way, that direction. But despite this, the magnet is so powerful that we can still sense some magnetic field even at this distance. We can see these magnetized maybe now paper clips, which I can maybe even try to disconnect them, and we can see that they stick together because of the, yeah. So, yeah. Okay. Yeah, so, yeah, yeah, this is an interesting way to show. So I can try to move this, but it goes back to the same direction, following the magnetic field lines. It made it, yeah. Maybe one more, yeah. Now I'm lost in the play here, sorry. So there are cases where the magnet is on, but we have no beam and people are still working in the experimental cavern. And this is really interesting to experience. It has happened to me a couple of times to have, yeah, that was too much weight. So because of these steel pads on the working shoes that I described earlier, since most of the structure in the experimental cavern is magnetic, you can actually feel the magnetic field while you are walking in the experimental cavern. And it's a very interesting experience. It's a sensation as though someone is trying to drag you to the sides whilst you are walking. Noemi is trying to pick up the paper clips. Yeah, let me do it. Okay. Any questions here? Any curiosities?
Another interesting fact is that not only for the safety issues, but also for the like screwdrivers, all the tools have to be non-magnetic, and bringing in a laptop is also difficult because close to the magnetic field they don't work. So working in that condition with the magnetic field on is not so easy.
We have some questions here in the room.
Go ahead.
Okay, thank you.
So my question is, what safety standard do you guys follow? Is that like OSHA, or is there some other safety standard that you guys follow in regards to, you know, what safety measures you use and what things you have in place in case things do go wrong?
So if you're referring to safety principles related to the radiation, which is present in the experimental cavern, then the general principle of dosimetry of the so-called ALARA principle, as low as reasonably achievable. So this is a principle which basically allows us to make a decision whether something is worth doing or not. But in general, work in the environment of the experimental cavern is pretty safe. I will show you the reading of my dosimeter when we go back to the surface later, and you'll see the value that's on it. And I've had it since a few months, and it's not higher than what you would get just anywhere in everyday life. Just taking a flight, actually, just one flight, would expose you to more radiation than spending a few months in the experimental cavern.
Does
the magnetism had like field gear or anything like that, like besides the field boots, field magnetism besides that?
Could you repeat that, please? Or
Like,
can you?
so like besides the steel boots and stuff, when you're like in the magnetic field and stuff, do you like feel it? Sorry.
Elton, the question is, do we feel the magnetic field other than where it's supposed to be, which is,
Other than steel. That's these boots.
oh, okay, without the steel boots?
Yeah.
You need a steel
No,
boot.
Mm.
Okay.
No, one cannot sense the magnetic field if one doesn't have magnetic material on their body. So there are some safety precautions during times such as this when the magnet is on. We have visitors which are allowed to come all the way down here, but we always make sure that these visitors, for example, don't have any medical implants in their bodies.
Electronic medical implants.
Like pacemakers.
We have one more question here so far.
How many errors do you guys get on average? You were talking earlier about that you had the precautions with that one, what do you call that, machine? How many errors do you guys have to fix on average?
Yeah, that's a very good question. And as you can imagine, from such a complex machine, you do get a lot of alerts, if not errors. So there are all sorts of technologies within the detector, as I said. And there are all sorts of failures, which can be categorized into hardware errors or errors in data taking. So you either have some, let's say, some value of some voltage which has gone to too much high of a value, or you might have some alert connected to the data. It's quite frequent, I would say. During a shift, you'd maybe encounter at least several such situations where you need to talk to experts and you need to debug the situation. And each situation is in a way unique. So we have millions of readout channels which come from different sources and so on. So if one of them breaks or gives inappropriate, let's say, data rates, which aren't physical, then you have to intervene. You have to speak to the people who are experts on that particular subsystem, etc. So yeah, there is, during the time that we spent in the control room together earlier, there weren't any, but the shift isn't as quiet as that made it seem. There are things to respond to all the time.
Yeah, and there are also errors not only from our experiment, but also from the tunnel itself, in the sense that we can have problems with the magnets, with the cooling. So it can happen, and it happens like once every few days on average, that we have to stop the beam and the collisions to fix some hardware problems that we get, and people have to physically go down and fix what's broke.
Right. And since Aurora, you mentioned now faults which occur with the LHC when it happens that we lose the beam. And this actually, again, as an exercise, I hope I'm not giving you too many exercises, but just as a thought exercise, the LHC is 27 kilometers in diameter, which means that these small bunches of particles have to traverse this distance, 27 kilometers, before encountering the opposing bunch with which they have to collide. But the size of these bunches is like billionth part of a centimeter. So tens of millions part of a millimeter. So it's microscopical, and you have to make them collide. Two such small bunches of particles collide with each other after they have traveled many times around this 27-kilometer ring. Any disturbance, even in the weather, can actually cause the magnets and the supply lines, which actually bend the path of these particles, to have small glitches and to deviate these bunches of particles. And this can cause what's called a beam dump. So we lose the beam. Typically in events of bad weather, this happens quite often. So this disrupts work for a few hours until beam is re-injected into the machine. Okay, so I think we've covered more or less what we could see in the service cavern. Slowly, we're going to go back up to the surface, calling the elevator now. Yeah. We might or might not stay online. Maybe Aurora, you can take over for the duration.
I show you what it means to when we say inject beam into the machine or to dump the beam. So you have seen the main tunnel, main LHC tunnel, which is this one, and it's 27 kilometers long. And I didn't say it before, but CMS is not the only experiment. We have 4 experiments along the tunnel, but this is just the last step. We start from here. Actually, we start from a bottle of hydrogen that we ionize, and then we have a small linear accelerator, then a first small circular accelerator, then we go into a bigger one, and then we inject into the main accelerator LHC. And this is because we start from particles that are still, they have almost no kinetic energy, and we have to accelerate them step by step. And for each step, we increase the size of the tunnel of the ring, and this allows us to go to a higher energy because there is a proportion between the radius that the ring has and the maximum energy that we can reach. Then we have all the collisions in the 4 experiments, and when we don't lose the beam for other reasons, like for technical problems, after several hours, can be 8, 12 hours, depends, we dump the beam on purpose. So we have special places in which we take the beam out of the ring and we dump it against a block of concrete because all the particles that are inside the bunches, not all of them, most of them have collided already, so the bunches are emptier than before and less useful for us, so it's better to inject new bunches. And the reason why we go against a concrete and we go against it not always in the same point is that the energy is very, very high. So we are back.
Yeah, so as promised, I'm going to show you now the reading of this device, which is the dosimeter. This is actually a passive dosimeter, so it doesn't have a display showing you in real time what the value of the radiation that you're exposed to is. But what you can do is periodically insert it into these devices, which are readers, and it immediately identifies and it starts reading the data that are on it. So you can see that the amount of radiation that I have been exposed to since I took this dosimeter maybe 5 or 6 months ago is 0.02 millisieverts. So that's 20 microsieverts. It's quite a small dose. As I said earlier, this is less than you would get just from a cross-Atlantic flight, just a single one.
Sorry for sticking my note. Indeed, the grand public can get something like 3 millisieverts per year, according to the European rules. So if we compare it to the 20 microsievert that you absorbed during the last half a year, that's nothing.
Yeah.
So usually we get much more, orders of magnitudes more from the environmental radiation. That's very important.
Indeed. Okay, so I think we can do 5 more minutes here on the surface where we can show you the place from which the detector was lowered in the underground more than 20 years ago now. So maybe we can get moving to that area and do some commentary there.
While we go there, if you have questions, feel free to ask them.
Question. Don't be shy, just.
No? Okay.
So earlier you said that the data gets filtered out. The uninteresting data, do you have like people review that over time, making sure that like the computers didn't miss something that they weren't accounting for or something?
No, because the uninteresting data are discarded, they're not saved, so we don't have a way to review them since we don't have them. It's problem of storage. We cannot save all the data, so we have to decide which one we want to save. And what we do is beforehand on the simulation, we try to see which event are interesting. We know which event are interesting. We try to see if our filters keep these events, and then we just trust our filters on the real data, and we review them with time, okay, if needed.
Okay.
You see now a picture
Yeah.
of the.
So this is a poster of, let's say, a cut of the CMS detector, and it is to size. I'm going to go a bit closer to it just for scale, so you can create an idea about how big the detector itself actually is in reality. So this poster is located 100 meters on top of the detector itself, which is further down the shaft. This floor that I'm standing on actually can be removed and is periodically removed whenever we have to lower something in the underground. And this is actually the place from which we lowered the different sections of the detector. If I don't remember if we accentuated this already, but the detector itself being such a big structure of 15 meters in diameter, so that's a 5-story building, and 20 meters in length, and it weighs tens of thousands of tons, it cannot, as a whole structure, be maneuvered and lowered into the underground. It's actually built like a huge Lego. So all of these subparts that you see, submodules in it, are actually integrated together. So they are built separately and they are integrated along this iron skeleton, which is called the iron yoke. Then we have this first level of integration where we integrate them into these big slices. And these slices were what was lowered in the underground. And then they were connected together. Such a delicate operation. So the heaviest of them, even the single slices, weighed up to several thousand tons themselves, up to a couple thousand tons. And this operation, Noemi is now showing you images from that time, took many hours, more than 10 hours to lower just one slice all the way to the underground. So if I wasn't here, but people who were explained that it was, if you were to see it in real time, you couldn't tell that it's actually moving. It was just moving 1 centimeter at a time. And it took half a day for the thing to get down safely. And everybody was anxious during this whole time, of course.
Yes,
Is it?
because it was the slices were just a bit smaller than the hole.
Yeah,
They
something
had to
like
be
10
very
centimeters.
precise. Yeah.
Actually, this happened because the most expensive, either you believe or not, most expensive part of such an experiment is the civil engineering. making the hole, the vertical shaft below Elton's feet bigger, let's say 1 meter bigger, would have increased the costs beyond the unacceptable. Obviously, every cent that we can save with the infrastructure we would spend on our detector. That's also very important.
Yeah. Yeah. So this saving on budget costs, people get to pay in anxious waiting for a few hours while the.
Well, of course, we could have let it down within 40 seconds, but nobody wanted that, really.
Yeah, sure.
It took something like 8 to 10 hours, as Elton said.
A bit in one piece.
Exactly, we wanted to land it safely.
Yeah. Okay, so one more thing I want to show you is one other poster which is in the same area here. We have a picture from above of the Geneva area where CERN is located and our experiment CMS is located. I'm gonna play a short laser animation on this poster now, which will show you the path of the particles from that initial acceleration that Aurora explained earlier. So they start first in this small ring, which is called the proton synchrotron. They acquire some energy there, and then they are injected in a bigger one, which is called the super proton synchrotron. They get accelerated even more, and then when they acquire the necessary energy, they get injected in the big ring, as you can see, which spans 27 kilometers in diameter. Here also, step by step, the particles, the bunches of particles, they acquire more and more energy. And once they acquire the maximum possible energy, they start colliding. And the collision point on top that you can see on top of the poster is where our experiment CMS is located. We can see that there are 3 more points where such collisions are going on. These are the places where the 3 other big experiments are deployed. So for scale, you can see here the Geneva airport, and you can see how much bigger the accelerator is even in comparison to the airport lane. Yeah, so I think we can head back to the control room now. We are low on time. In the meantime, please ask questions.
Thank you. Zoltan, Noemi and Elton, thank you so much for an amazing tour. Everybody had great fun, and we have, yeah.
Yeah, thank you very much for being such attentive listeners to all the students there and for asking wonderful questions. And yeah, I hope to one day have them here at CMS working with us.
Absolutely. We still have some questions, so we are going to wind up with that because we are also running a little bit late here. So, but this is exciting to have students' questions.
Yeah.
So from all the data collected from the machine, about what % of it does the computer deem as important?
Yeah, that's a good question. So in the first stage of this filtering, less than 1% of the data is kept. Then once it's this less than 1% is sent to the surface for further processing, then we have a second stage. As I mentioned, there is a high-level trigger, as it's called, which does a more thorough processing or pre-processing of this data, and then makes a further decision, which reduces maybe 100-fold once again the amount of data.
We have 1,000 that survives this high-level trigger out of the 40 million
yeah.
at the input. So you might imagine this is a very, very huge reduction. This goes up to something like 400 megabytes per second as the data output of the experiment. And this is something that still can be handled. Without that, if we would want to read out our more than 120 million data channels 40 billion times per second, that would be something that obviously technically, well, when the experiment was designed, it was technically impossible.
Yeah.
Today it is still hardly possible, but what we wanted to suggest with this kind of filtering trigger is that obviously we are not losing important data. Fortunately, the nature works in a very, very helpful way. Most of the collisions is, as we call, elastic scatterings. In elastic scatterings, the two protons might disintegrate, of course, but their partons will not change their identity. There will be no particle to energy, energy to particle transition that we are interested in. That's the so-called deeply inelastic scattering. And all these filtering, all these trigger is set up to trying to make a difference between the elastic and the inelastic scattering. One is, for example, the muons. It's my favorite stuff. I come from muons, sorry. The thing is that within the proton, you might have many different particle types, except the muon. If you see a muon flying out at the correct time from the interaction point and by the muon system, you can be almost 100% sure that something interesting happened. Actually, there are more than 50 other criteria for this. For me, the muon is the easiest to explain. I apologize for that. But if the muon system tracks a muon during the collision, the individual muon detectors can discuss it very quickly and easily among each other. These are usually electronics that is FPGA based and deployed on the detector front end directly. And this decision can be made very quickly. And then, as Elton said, this event that survives this kind of filter is read out from the detector and pumped up to the computer farm, where the whole detector is taken into account, the data from, and the so-called signature of the event is going to be investigated. There we have an enormous time. That's something like 100 microsecond to make a decision whether the event is interesting or not. And of course, we have enormous number of CPUs, something like 15,000, according to the present system, that to make this decision. So obviously, the question, one of the previous questions was about whether we are whether there is a threat to lose anything interesting or not. This is always a dilemma. Our groups are working on very hard to exclude this as much as possible.
Yeah.
But of course, this dilemma is always there.
There are different approaches to tackle this. There are also a couple of systems that we have deployed here in CMS, where we actually store data from all events, but in very small quantities. So we skim just the surface, let's say, of each event. This is called data scouting. It has been implemented in recent years to tackle these issues that Zoltan was telling about. And since you mentioned event signatures, this is a perfect setup for what the students are going to be doing for the remainder of the day. They are actually going to analyze data from the CMS open data, and they are going to identify. So basically what you're seeing on the screen right now is what you're later during the day going to analyze events of this kind. You're going to learn to identify different tracks, what particles they belong to, and to identify the processes that gave rise to them. So yeah, I wish you happy particle hunting for the rest of the day.
We have two quick questions, two more quick questions, so please go ahead. We're running very late.
What sort of stuff do you lower down to the detector?
Pardon, could you repeat? I didn't get it.
What sort of stuff do you lower down to the detector? You said earlier that the floor opens up periodically to lower stuff down. What sort of stuff is that?
Let me answer. So the question here was, what kind of stuff do you lower down into the cavern, basically?
Oh, yeah,
So,
that's quite that's quite good awareness of what I was saying. So yeah, when I was next to the poster, I said that we remove periodically the floor there in order to lower things. Of course, we don't add, or at least we have lowered the detectors 20 years ago. But what we need to work on the detector is these machines like scissor lifts and cherry pickers in order to reach the upper parts. So you can imagine something gets broken on the upper parts of the detector. You cannot just reach it from the floor. And that's why we need these devices like scissor lifts and cherry pickers, which are the main ones that I can think of now, which are lowered using the cranes.
Also, in 4 years, we will start with a new phase of the LHC called ILUM LHC, and we will upgrade the detector starting from the end of this year up to 2040. So we'll bring down new parts of the detector to replace some of the existing parts that will be removed.
And related to this about the devices or the machines that we periodically bring up to the surface and then lower back down when we need them, some people ask related to this, why don't you just leave them in the underground and don't have to deal with this? Well, actually, most probably the electronics in these machines wouldn't survive the high radiation environment over there because these are commercial, let's say, machines which are not made to endure such an environment. Yeah, that's why we need to keep them safe on the surface while there is radiation there, and when we need them, we lower them.
So my question is, in 2012, you founded the boson. So what's next for CERN, essentially? Like, what are you guys trying to discover now?
Yeah, that's a very good question. I mean, the culmination of the effort, of course, was the discovery of the Higgs boson. But the CMS experiment, like the other big experiment on the LHC Atlas, are what's called a multi-purpose experiment. So the range of the physics program is very wide. So you have people working on analysis starting from precision measurements of the standard model, which is this theoretical model completed by the discovery of the boson. But then you have people doing searches for dark matter candidates, for example. So these are particles, theoretical at this point, which might account for the dark matter in the universe, which is one of the biggest mysteries of contemporary physics. Have people looking for all sorts of signatures which would indicate of new physics or physics beyond this theoretical framework that we have currently. So yeah,
Since it's not, we have it, it works, but not perfectly. There are things that are not super clear or doesn't work as expected. So we still have to dig more into it, understand this corner case that not go according to our theory.
So, I mean, in summary, there's a very wide program. Whatever you're interested in, I guess you can find some analysis which fits your preferences. We publish a lot of papers, and yeah.
thank you so much again for this amazing virtual visit, which took us to the real stuff, to the real deal. So we are gonna try to analyze the data today and figure out, maybe they are gonna find some Higgs bosons, who knows. So thank you again so much for this wonderful visit. And I'll catch up later with you, Elton, Noemi, Zoltan. Hey.
Thank you. Bye.
Bye.
Thank you. Thank you. Have a nice day. Bye.
Appreciate everyone. Bye.